I don't know if you guys have ever heard about this concept of free energy. When you first hear about it, it seems kind of weird. It's actually a kind of a man-made contraption for us to try to get a handle on whether or not some kind of change will be spontaneous or non-spontaneous, would like to happen or would not like to happen. One way to define free energy, it's always given this symbol G or delta G, the change in free energy, is simply to combine, in a sense, the change in enthalpy and the change in entropy by this famous equation. Memorize this one in the red box. This one's nice, interesting, but I don't honestly use it very much. It compares the entropy change in the universe to the change in free energy in the system based on dependent on temperature. This one's much more common. Another way I've heard to define free energy is some kind of measure of the total energy content of the system. But my goodness, that's hard to quantify sometimes. But it's not hard to quantify the change in enthalpy and the change in entropy during a particular chemical or physical process. I'm actually going to leave most of this for another video, but these delta G of formation, there should be perhaps a little F down here. These free energy numbers are associated, or tabulated I should say, for us in the back of the textbook or various tables throughout the throughout the world. So we have tabulated free energy numbers. The free energy of formation for pure elements is zero, because if I was going to form hydrogen gas from hydrogen gas, there's no free energy change associated with that. So this reminds me that I could use delta G of a reaction, delta G of a system, equal to the delta G of formation of the products minus the delta G of formation of the reactants. But like I said, that's for a different video. For here right now, I want to show a couple of examples of how I could actually use delta H and delta S to find delta G, the change in enthalpy, the heat flow, and the change of entropy, like disorder or chaos. Many of my other videos have talked about how you could possibly find delta S or predict delta S. So hopefully you've had a chance to look at those as well. But we know from Gen Chem 1 that if the delta H is positive, it's endothermic. And if it's endothermic in terms of heat flow, that's not particularly favorable. Delta S being positive, on the other hand, is favorable. That means this change in the system is more entropic, more disorganized in a sense. Although the delta S is almost always given in joules per Kelvin, and the delta H is usually given in kilojoules per mole. But let's try a few of these. This brings up the idea that it's temperature dependent as well. So the temperature fits in along, the Kelvin temperature fits in along with the entropy change in a way something like this. So if my delta H was 18 kilojoules, and my delta S was, we said 60 joules per Kelvin, the Kelvin temperature comes into play as I want to multiply by the delta S and the Kelvins cancel. So I could write it as an inequality saying, for this to be spontaneous, I want my free, by the way, delta G and delta S follow similar conventions. For the delta H to be favorable, I would like it to be negative, that is exothermic. For delta G to be favorable or spontaneous in the forward direction, I would like it also to be negative. Delta H and delta G are often similar in sign because delta H is in kilojoules and delta G is in kilojoules, and delta S is usually given in joules, or perhaps I should say, unless the temperature is extreme, then the delta S term is usually of less of a factor than the delta H term. In other words, the entropy is less of a consideration than the enthalpy change. But again, it depends on what temperature. So if I want this delta G to be negative, I want to set this minus this to be negative. Solve the inequality. Did I do this correctly? So what do? I shifted the minus T delta S term by adding it to both sides to this side. Therefore, 18 kilojoules is greater than 0.06 kilojoules per Kelvin times the Kelvin temperature, and the Kelvin temperature solves to be 300-ish. So anything, wait a second, what did I say here? Thus, for any temperature, the temperature should be larger than 300 Kelvin in order to allow the delta G to become negative. We could scroll back up here and take a peek at that again. So this is not favorable, this is favorable. But this term is in joules and it's less of a factor than this term unless my temperature gets pretty hot. So take 500 Kelvin. 500 Kelvin times 60 kilojoules, 500 times, oh geez, is that 3,000? I think it's 3,000. No, that'd be 30. Yeah, 3,000. It'd be 30,000, I believe. So 30,000 joules per Kelvin. Actually, the Kelvins cancel. 30,000 joules is 30 kilojoules, and 30 kilojoules negative would overwhelm this positive 18 kilojoules and leave me with negative 12 kilojoules, if I'm thinking about this correctly. So if I can get this delta G to be negative, that is to say, come up with this term so that it overwhelms this term. Anyways, it's going to take a lot of practice with this. Let's do some more of that. It's so much fun. Particular chemical reaction is delta H of negative 53 and a delta S, kilojoules, delta S of 75 joules. Temperature is 300. What's the free energy change? Well, oh yeah, by the way, delta H and delta S are tabulated for us in tables for particular, formations. But they do change slightly when we move away from standard temperature, but they don't change that much. So usually we actually ignore that. If I put that 53 kilojoules here and that 75 joules here, in other words 0.075 kilojoules per mole Kelvin, Kelvins cancel. This should really be kilojoules per mole, but whatever. I know I'm sloppy there. But the 53 minus this 22 and a half, this time this is 22 and a half, becomes even more negative, more spontaneous. Excuse me. So we could say that the negative enthalpy, the delta H being negative here, drives the reaction forward, but also the positive 75 is more entropy, and that drives the reaction forward. So both the 53 kilojoules being negative for the enthalpy change and the positive 75 joules for the entropy change drive the reaction to be fairly spontaneous. Here's a good question. Zinc and hydrochloric acid, it's exothermic because the energy is written on the right hand side. And also, I'm noticing I have no moles of gas here, no moles of gas here, and I have 1 mole of gas over here. So whenever I can form 1 mole of gas or more increasing number of moles of gas, what does that say about the entropy? Jeopardy music. Oh yeah, it's positive. So my enthalpy, exothermic, would be negative, and my entropy, gaining more moles of gas, would be positive. So part 2, or choice 2, which has my enthalpy being negative, and choice 3, which my entropy being positive, both of those actually drive this reaction forward. If I had numbers, I could plug them into the delta G equals delta H minus T delta S. Would you predict the delta G to be positive, negative? Oh yeah, well, if I know if I add a metal to acid, it goes forward, so I already know the delta G is going to be negative. But how can I argue that to be the case, knowing that delta H is negative and delta S is positive? If delta H is negative and delta S is positive, this reaction will always want to be spontaneous. Any reaction with the negative delta H and positive delta S, both of those are favorable. And so I'm going to say that delta G is also favorable forward, and that's to say it'll be negative. Again, if this is the first time you've heard of this, it's ridiculous double talk, right? So what's happening here? I'm reacting hydrogen gas and oxygen gas, probably in an explosion, not necessarily, but probably in an explosion. Explosions are exothermic. So what do you suppose about delta H for this reaction? Oh yeah, it's negative. Enthalpy, right, enthalpy energy released. And what about delta S? Oh wait, it says determine the signs So what about the delta S? Would delta S be positive or negative here? And your ability to answer this question depends on you having watched those other videos already. But here I'm forming fewer moles of gas, 2 moles of gas and 1 mole of gas, a total of 3 moles of gas on the left-hand side, 2 moles of gas on the right-hand side. Forming fewer moles of gas implies that I will have a negative entropy change. So I'm talking the delta H is negative, and the which is favorable. Delta S is positive. Oh, no. So delta S is negative. So I'm looking for a negative and a negative. How about this? And what about spontaneity? Does hydrogen gas want to, if I dare personify them too much, react with oxygen gas? And the answer is, yeah, you put a spark to it and you're going to see an explosion for sure. So aside from the fact that you need some activation energy, the reaction does tend to go forward in the forward direction. So the choice here is G. They're all negative. Interesting. Let me launch back in. Let me kind of backpedal a little bit. We've actually seen this reaction, we've seen this equation, products minus reactants, and we've seen this equation, products minus reactants. And now you get a sense of how I could probably use them. Use this one to find the delta H, use this one to find the delta S. Enthalpies of formation under standard conditions of products minus reactants. Entropies under standard conditions of products minus reactants. Combine those two answers to get the delta G. Again, the delta G is some kind of measure of the spontaneity, the likeliness of a reaction wants to go forward. Yeah. So tabulated delta H of formations for the reactants and the products, and the the standard entropies in joules per mole Kelvin for the reactants and products. So do you know what to do? I made a cute little table here with the balanced chemical equation. I put the heats of formation underneath each compound, and I say products minus reactants, and the balanced equation, the stoichiometry of the balanced equation is important as well. So 6 of these and 6 of these make 1 of those and 6 of those. So I included the 6s, 6 of these and 6 of these. Those are the reactants, and the products are 6 of these, but you knew that enthalpy change was 0. That's a pure element. And I get values of, what do I go? Ooh, did I even solve it? I don't think I didn't even write down the answer. I didn't write down the answer for this, but it is 2805 positive. Whoa, so this is not favored in terms of enthalpy. Is it favored in terms of entropy? This answer looks like it came out to negative 262 joules per Kelvin. Looking at this right here, if that's what I've wrote is correct, and negative entropy change is also not favorable. So if I'm subtracting a positive, that makes this second term positive and the first term is positive. So enthalpy being positive is not favored, and entropy being negative is not favored, because it makes my free energy very positive. And so this will never want to happen by itself. But plants magically do it. They make sugar out of carbon dioxide and water, spitting out oxygen gas as a waste product. Interesting. But it's not done in one simple chemical reaction. It's a series of very complex steps. One more example or you could pause the video and pretend like I didn't see that down there. There we go. So my products minus reactants of my enthalpies and my products minus reactants of my entropies, and I'm at 298 Kelvin. And you could pause the video if you want more practice with this right now, because you know I'm about to show you the answer. Or not, because here's the answer. So products minus reactants, and the only way for you to get good at this is to sit down with it and try it. So if you didn't pause the video and you didn't try it, shame on you, but here's another example. So 4 NOs, 6 H2Os, 4 NOs, 6 H2Os, 4 NH3s, 5 O2s, 4 NH3s, 5 O2s, and that gives me the enthalpy as being negative. Looks like the entropy is positive. Negative enthalpy change is favored. Positive entropy change is favored. So I'm pretty sure my delta D is going to be negative. So if this term is negative, and I'm subtracting a positive, that makes this 908 even more negative, down to negative 962, and so we'll say it's very favorable. Oh, is there more? Oh my lord, I'm not going to go over it. You guys can go look at it if you want to. It's the same song and dance, products minus reactants. Yeah, and that's how we do that. Well, it's one way to do it. The other way to find the free energy is to have to know the free energy of formations of the products minus reactants, in which case we have an equation that says delta G of reaction under standard conditions equals the summation of the delta G of formation of the products minus the delta G of formation of the reactants. Excuse me, frog in my throat. Alright, but enough of that. Enough frivolity. Enough video watching. Thanks for watching, and I'll see you soon in class, I hope.